Welcome to our quantum deep dive. For every single particle of matter in the universe, there should be a perfect mirror image, antimatter. But if that's true, where is all of it? Today, we're diving deep into one specific family of these mirror particles, the antileptons, to see if maybe, just maybe, they hold the answer. This entire explainer is based on a fantastic essay by Jörg Oeschnepat.
So, let's start with the big question that's really at the heart of all this. What does it actually mean for a particle to have a mirror image? I know it sounds like something straight out of science fiction, but it's one of the absolute cornerstones of modern physics. Okay, let's get into it. You have to go all the way back to 1928. A brilliant physicist, Paul Dirac, is tinkering with his equations, trying to describe how electrons behave. And his math, well, it spits out this completely startling prediction. For every particle, there has to be an antiparticle. And this wasn't just some mathematical quirk. This antimatter, as he called it, would have the exact same mass as its regular twin, but it would totally flip the script on other properties, like its electric charge.
And this is where that whole mirror image idea really clicks. So take the family of particles we call leptons. They have either a negative or neutral charge, and this quantum property called a lepton number of +1. Now look in the mirror. Their counterparts, the antileptons, have a positive or neutral charge and a lepton number of -1. See? It's a perfect flip. The most famous example, of course, is the good old electron, a building block of you, me, everything. Its mirror twin is the positron, a building block of antimatter. Same weight, opposite charge. It's that simple and that profound.
Exactly. So now that we've got the basic idea down, let's actually meet the whole family. Who exactly are the members of this exclusive and kind of exotic anti-lepton club?
Well, you can see just how beautifully organized this family is. Just like regular matter, antimatter is sorted into 3 generations, and each one is heavier than the last. The first generation gives us that positron we just talked about, along with its ghostly little partner, the electron antineutrino. Then you get to the second and third generations, and you find these heavier, more exotic cousins, the antimuon and the anti-tau. And of course, each one has its own corresponding antineutrino. It's like a perfect, symmetric family portrait.
And these family members have really distinct personalities, let me tell you. The positron was the very first one ever spotted in an experiment, which was a huge deal back in 1932. It proved Dirac was right. The antimuon, well, that's the heavyweight middle child, more than 200 times heavier. And then there's the anti-tau, the super heavyweight champion, tipping the scales at almost 3,500 times the positron's mass. And then you have the antineutrinos. They're the elusive ones. No charge, barely any mass, and they pretty much ignore all other matter. They just ghost right through everything, which makes them incredibly hard to even spot.
Okay, so these particles are real, but they're clearly not just lying around. I mean, if they were, we'd have a serious problem, since matter and antimatter annihilate the second they touch. So, where on Earth do they come from, and how long do they even stick around before they disappear?
Let's talk about stability, or the complete lack of it. The antimuon has an average lifespan of just 2.2 microseconds. That's 2.2 millionths of a second. It's a fleeting existence, to say the very least. You blink, and you could have missed its entire life a million times over. But that antimuon is practically immortal compared to the anti-tau. Its lifespan is a staggering 2.9 times 10 to the minus 13 seconds. It vanishes in less than a trillionth of a second. It's just gone. The takeaway here is pretty clear. Other than the positron, which can be stable, these mirror particles are unbelievably fleeting.
Right, so given their incredibly short lives, their origins are, as you might expect, pretty dramatic. They're born from cosmic violence, when super high-energy rays from deep space come screaming in and smash into our atmosphere. They also pop up in certain kinds of radioactive decay here on Earth. And of course, we create them ourselves in our most powerful machines, particle accelerators, where we basically use Einstein's famous E=mc² to turn pure energy into pairs of matter and antimatter. And maybe most amazing of all, deep inside the fiery hearts of stars and exploding supernova, unimaginable numbers of antineutrinos are forged and flung across the cosmos.
From cosmic explosions to something much more down to Earth and incredibly useful. It might sound crazy, but one of these antileptons, the positron, has actually become a key tool in modern medicine. It's saving lives every single day. Yeah, the technology is called a PET scan. That stands for positron emission tomography. It all starts when a patient is given a special tracer liquid, usually a type of sugar that's been tagged with a radioactive isotope that just so happens to spit out positrons. And the really genius part is that your body's most active cells, like in your brain or unfortunately in tumors, are the hungriest for this sugar.
So, once that tracer gets absorbed by those hungry cells, the radioactive isotope inside starts to decay, and it releases a positron. Now, you have to remember, this positron is an antimatter particle floating around in a universe made of matter, your body. It doesn't get far, maybe a millimeter or so, before it inevitably bumps into one of the countless electrons in the tissue all around it.
And then the inevitable happens. Matter meets antimatter. The positron and the electron don't just collide, they completely annihilate each other. Both particles just vanish. They cease to exist as matter entirely.
But their mass isn't just lost, it has to go somewhere. And it does. It gets converted into a tiny flash of pure energy, exactly like Einstein's E equals mc squared predicted. This flash isn't just a random burst of light either. It very precisely forms two high-energy particles of light called gamma rays. And physics demands that these two gamma rays always have a very specific energy signature, 511 kiloelectron volts each.
And here is the absolute genius of the whole technique. Those two gamma rays fly away from that annihilation point in precisely opposite directions. A big ring of detectors surrounding the patient is designed to spot these pairs of rays that arrive at the exact same instant. By tracing these lines back to where they cross, a computer can pinpoint the exact location of that annihilation event. Do that millions of times, and you build up a stunningly detailed 3D map of all the metabolic hotspots in the body. It's amazing.
Okay, so from saving lives to trying to understand why life itself, and really the entire universe, even exists, antileptons aren't just for medical scans. They might actually hold the key to one of the biggest, most fundamental puzzles in all of science.
And this really is the heart of the mystery. All of our best theories, what we call the Standard Model, tell us that the Big Bang should have produced a perfectly balanced 50-50 mix of matter and antimatter. But if that had happened, they would all just annihilate each other in a blinding flash of light, leaving behind a cold, empty universe. But here we are. We live in a cosmos that is overwhelmingly made of matter. So, the billion-dollar question is, where did all the antimatter go?
Well, the physicist Andrei Sakharov figured out that for this to happen, for matter to win the day, three very specific conditions had to be met in the early universe. First, some process has to exist that can break the one-for-one rule, a way to make matter without an equal amount of antimatter. Second, nature has to have a slight preference for matter over antimatter. That mirror image can't be perfect. There has to be a tiny flaw in the symmetry. And third, all of this had to happen and get locked in during the chaotic furnace of the Big Bang before the universe cooled down and all the rules became fixed.
And this brings us right back to our heroes, the leptons and the antileptons. One of the leading theories out there, called leptogenesis, proposes that the original imbalance, the first tiny crack in that perfect mirror, wasn't in the heavy particles, but in these light ones. It suggests that way back in the early universe, some process that met all of Sakharov's conditions created just a tiny fraction more leptons than antileptons. And later on, other processes converted that tiny surplus into the matter-dominated universe we see today. Think about that. Our very existence could be the result of a tiny hiccup in the antilepton population right at the dawn of time.
That is an incredible theory, but is there any actual evidence for it? To find out, scientists around the world are building some of the most ambitious, most massive, and frankly, most mind-blowing experiments ever conceived, all to study the subtle behavior of these incredibly elusive particles. And the scale of these projects is just wow. At CERN, they're literally trapping antiprotons and positrons to build antihydrogen atoms, just to see if antimatter falls up or down in a gravitational field. In the United States, the DUNE experiment is going to fire a beam of neutrinos and antineutrinos straight through 1,300 kilometers of solid rock to see if they behave even slightly differently. That's a direct test for that flaw in the mirror. In China, the Juno experiment is a gigantic underground sphere designed to untangle the neutrino mass mystery. And at the South Pole, the IceCube experiment uses an entire cubic kilometer of pristine Antarctic ice as a giant detector to catch high-energy antineutrinos from exploding stars light years away. And all of this unbelievable work is aimed at solving a few fundamental unknowns. We still don't know the exact mass of any of the antineutrinos, we just have some upper limits. And there are these tantalizing hints that there might be a fourth kind of antineutrino, a so-called sterile one, that might not interact with anything at all except through gravity. Finding either of these would completely rewrite our understanding of physics as we know it.
Which leaves us with a final, pretty mind-bending thought to chew on. The laws of physics seem to demand this beautiful, perfect symmetry between matter and its mirror image, and yet, the universe we live in appears fundamentally asymmetric. So, if every single particle has a perfect counterpart, could our entire universe have one too? A mirror universe out there somewhere, made entirely of antimatter, where its own cosmic mystery is trying to figure out why there's so little matter? It's a fascinating question, and it's what drives physicists to keep digging every single day.
And that's all the time we have for this explainer, which was inspired by the work of Jörg O.S. Schneepat. You can find more at his website, schneepat.de.
Thanks for joining us on this deep dive.
Schneepat.de is a private project by Jörg O.S. Schneepat dedicated to promoting quantum technology. Its mission is to present knowledge in a way that is clear, precise, and transparent for those just starting out, as well as for experts who wish to deepen their expertise. He firmly believes that education and access to well-structured information are the keys to unlocking the full potential of this future technology. If his work helps you realize your own visions and actively and consciously shape quantum technology, then the goal of his project has been achieved.